The points P, Q, R, and S given here form a parallelogram in R3. We would like to find the area of this parallelogram, and at first it's not clear the relation of the sides to each other. So for example, this could be PQ, and we could have RS like that, and so the parallelogram could be generated by the vectors PQ and PR, or maybe R and S are switched, so we could have PQ and then SR, and so then PQ and PS would generate the parallelogram. And without doing a more detailed analysis, especially to figure out the diagonal, which I think it's actually pretty clear from these numbers that P and R are the 2 points that are furthest apart. Take a look at the numbers in there for a moment, and you'll probably agree with that. The difference in the coordinates is the most between P and R. So actually this one is the correct parallelogram. So the one that we seek is this. But let's compute both of them and see what happens. So to find the area of a parallelogram, it turns out that this is an application of the cross product. The area determined of the parallelogram determined by PQ and PR. So the area of the PQ PR, I forgot the P there, PR parallelogram is given by the absolute value, the magnitude of the cross product. When you write the symbol these absolute value bars, you have to consider what's inside. What's inside here is a vector, and so they're not actually absolute value bars. They're telling you the magnitude of the vector. Okay, so we need the vector PQ, the vector PR, and then we need the absolute, the magnitude, excuse me. I keep doing it, the magnitude of the vector. Okay, so PQ, what is the vector PQ? PQ is the vector. Take the coordinates of Q and subtract the coordinates of P. So 3 minus 1, 3 minus 0, 3 minus 2. So that's PQ. And what is PR? Take the coordinates of R and subtract those of P. 7 minus 1, 5 minus 0, 8 minus 2. So 656 is PR. So now the cross product, PQ cross PR, and it doesn't matter which order we do this, you will get a different answer, and there'll be negatives of each other, which is what's making me think of absolute value here. But the two vectors that are negatives of each other will have the same magnitude. Okay, so PQ cross PR is equal to the determinant of the matrix. We'll put I, J, K across the top row. PQ is 2, 3, 1, and PR is 6, 5, 6. So this is just this problem is an excuse to do a cross product, although this is not a terribly important application of the cross product in calculus 3. It's just that we're learning the cross product, and so we want to calculate the cross product using this determinant formula. The main property of a cross product is that it will actually give us a vector which is perpendicular to both of those. That's extremely important when we're analyzing surfaces and tangent planes and planes in general, because a plane is actually determined by a single point and a vector which is perpendicular to it. Okay, let's calculate this determinant. It's going to be I times the determinant of this 2 by 2 here, which is 18 minus 5, so that's 13, and then minus j times the determinant of, take away the j row and the j column, you're left with 2166. So 2 times 6 minus 1 times 6 is 6. And then plus k times, remove the k row and k column, and you get this little 2 by 2 here. 10 minus 9 is 1. Sorry, that's 10 minus 18 is negative 8. So let me just double check my arithmetic on these. The I coefficient is 18 minus 5. The j coefficient is 12 minus 6. And the k coefficient is 10 minus 18. Okay, so that's PQ cross PR in component form. We have 13, negative 6, negative 8. And then the magnitude of that vector will give us the area of a parallelogram. That is not the parallelogram we seek, though. We want PQ, PS. We don't know that yet, let's say. Okay, so our magnitude is the square root of 13 squared plus negative 6 squared plus 8 squared, and that's 100, so 269. And I think 17 squared is 289. So that's not a perfect square that I know of. And I don't know if there's a perfect square in there or not. Let's just leave it as the square root of 269. And let's compute the area of the parallelogram from PQ and PS. So that's going to be the magnitude of the determinant of, I'm not going to put the arrows to save time here. We need PQ. I think we did PQ already. PQ was 231. And now we need PS. We haven't looked at PS. PS is 4, 2, 5. 4, 2, 5. So this is going to be I times 15 minus 2 is 13. We need the magnitude of this. And then minus J times 10 minus 4 is 6. And then plus K times 4 minus 12 is negative 8. And I'm feeling like that's exactly what we had here. That is, it's exactly this happens to be, what a coincidence. It's exactly that. So we're going to get the same answer. The square root of 269. So we couldn't go wrong. Is that just a coincidence, or is that, will that always happen? If you have a parallelogram in 3 dimensions and you take any two sides and you do the magnitude of the cross product, you'll get the area. Let's take a look at that. We have P, Q, and R was over here, and S was here. This was our parallelogram. And then we also looked at the parallelogram that was PQ cross P, the PQ-PR parallelogram. What is that parallelogram? It still has this side PQ, but now it has PR. So it's this parallelogram. And these two parallelograms have the same base, PQ, and they have the same height. The height is the distance between this side, SR, and this side, PQ, which is the same as the distance, the vertical distance between this side is just an extension, a horizontal extension of SR. So the vertical distance between this horizontal extension and PQ is exactly the same as SR and PQ. So these two parallelograms will always have the same area. And this is an illustration of something called Cavalieri's principle, which says if we take cross sections of this parallelogram and then we shift them, shifted cross sections of that parallelogram won't change the area, and we can shift these horizontal cross sections to being in the red parallelogram. The distance between the two red sides here and here, for example, is exactly the same as the distance between P and Q all the way up. And same for the blue parallelogram. The distance between two opposite sides in these horizontal cross sections is just the magnitude of this horizontal line, the length of this horizontal line segment. So they have the same cross sections all the way up, and so they'll have the same area. It's like taking a stack of coins. If you have a stack of coins and then you shift them by putting them like this, same number of coins, so it should be the same height. Then if you imagine this in two dimensions, there's an area, and here there's an area, it's the same area.